So I need to say a little bit about some large-scale issues having to do with geometry. So we understand geometry a lot better these days than the 17th and 18th century people did. We have a broader appreciation for the large-scale scope of geometry, that there's not really just one geometry, the geometry of the world in which we live in. That's actually somewhat debatable, what that actual geometry is. There's actually a lot of different potential geometries, and there's relationships between those geometries, and some of them are a little bit more fundamental than others. So in the 19th century, this view started to develop that sort of at the heart of things, the simplest kinds of geometries were the affine geometry and the projective geometry. Now, we've seen them already. The affine geometry is basically just the geometry that you get when you're only allowed to think about parallelism. And projective geometry is in some sense even more simple-minded. You can't even talk about parallelism. You only have points and lines and incidents. Now, to get more sophisticated geometries, like say Euclidean geometry, we can take one of these geometries, typically affine geometry, and impose additional structure. For example, we can add the notion of perpendicularity. We can say, let's agree that we know what perpendicular lines are. We can also add the notion of measurement, for example, say distance, or in rational trigonometry, quadrants, giving us a way of measuring how far apart points are, or perhaps lines are. So with these added aspects, we get a richer kind of geometry. We could call them metrical geometries. Prominent among them is Euclidean geometry, the familiar geometry that kids learn in school. But there's also variants. There's relativistic geometry, which in the 20th century has become more and more important, and now arguably is just as important as Euclidean geometry, if not actually more important in terms of understanding the world in which we live in. But there's also spherical geometry and hyperbolic geometry. These are other kinds of metrical geometries, maybe coming from projective geometry a little bit more. And it's important to understand that the rectangle area formula that we started our discussion with really lives in this region. Okay? It's something that you're able to introduce after you have defined perpendicularity and after you have introduced the notion of distance. Because you don't have rectangles until you have perpendicularity and until you have these distances to measure the base times the height. Okay? So the rectangle area formula, which is usually assumed to be the fundamental formula in calculus, already requires a relatively sophisticated geometrical framework. But area does not, in fact, need perpendicularity or distance or quadrants. It is actually already implicit in affine geometry. This is something that the 19th century mathematicians understood, but perhaps because geometry is not studied quite so much these days, people don't really appreciate this. But area really does not live at this realm. Area actually lives up here. Okay, it's actually a concept from affine geometry. It's a hugely important understanding, okay? Affine geometry is really a natural context in which area makes sense. Once you have parallelism, then affine geometry gives you a notion of area. Okay, so there's a very, very crucial understanding that calculus is really potentially already at this more introductory level. We do not have to go down to these metrical geometries to establish calculus. The ingredients are already here in affine geometry, otherwise the geometry of linear algebra. Same thing, really. So let's make sure that we all understand this point. Why is it that just from affine geometry there is naturally a God-given notion of area, more precisely relative area? Okay, so the reason is this, that in affine geometry, if we start with two lines, say the x-axis and the y-axis, like we have so far, And we consider two other lines which are parallel to those, say this one here and this one here. So we have two parallel lines in one direction and another pair of parallel lines in some other direction. Then those four lines determine where they meet a little parallelogram. And we've seen in the discussion around our first lecture that those four parallel lines can be extended to give us a series of equally spaced parallel lines in this direction and in this direction. So once we have these two lines, we can, using this line here as well, create another line which is equally spaced, and then another line which is equally spaced, and so on. So we're able to extend the original two lines to a family of equally spaced parallel lines in both of the two directions. That means that now the plane is covered with all kinds of parallelograms, each one of which is a translate of, say, the original one. And that's really telling us that we already have a notion of area. Because we can just declare that the area of this thing is going to be the same as the area of this one, same as the area of this one, same as the area of this one, and so on. So if we want to compare the area of this one with the area of this one, then since this one consists of three parallelograms and this one consists of one parallelogram, we can safely say that the green object has 3 times the area of the red object. So we get actually a notion of relative areas, and at least approximately. I mean, exactly if you're just working with lines that are in these directions, but if you have some more complicated figure, you could sort of subdivide it into lots of little parallelograms in this direction, and then you could compare this arbitrary region here with another arbitrary region. So I might just say a little bit about that. So once you have a family of parallelograms that sort of tessellate the plane like this, it's not too hard just by drawing some diagonals and getting midpoints to subdivide each one of them, say, into 2 if you feel like. Okay, you can subdivide each one 2 in this direction as well. So it's not too hard to sort of go one level further and then have all of these parallelograms divided into 4 smaller equal kind of parallelograms. So we can create this family of parallelograms which are tessellating our plane very finely if we want. Okay, and that gives us a lot of control. We can actually approximate 2 given regions in terms of their areas just by counting numbers of little parallelograms in 1 and number of little parallelograms in 2 and comparing those 2 numbers. Okay, so crucial insight that the notion of relative area is really already encoded in affine geometry. You do not need a notion of perpendicularity, and you do not need a prior notion of distance or lengths to measure the separation of sides of rectangles. All right, that means that calculus can be established in an affine setting. In other words, the language, the framework of linear algebra. So there is a crucial area formula that I want to tell you about. But in order to tell you what that is precisely, I need to establish a little bit of notation and terminology having to do with some basic shapes or figures in the affine plane. So these objects are going to be called sides and triangles. Okay, so we're going to make some definitions here. And we're also going to introduce some notation that will support these definitions. So the first definition is that of a side, like the side of a triangle, say. What do we mean by the side of a triangle? So our definition is going to be that a side, say AB with a bar over it, is a set consisting of a point A and a point B. In other words, it's a set of 2 points. That's what a side is. A point is like an affine point. We're talking about the 2-dimensional situation here, so that's the context. So if you have a set of 2 points, then that is a side. An oriented side, which will be denoted by AB with a tilde on top, is an ordered set of 2 points. It's a set that's ordered, has a first element and a second element, denoted by that comma. Now I have to say something a little bit about terminology for data structures. That's quite close to my heart, but will not be familiar to a lot of you. Okay, so when we're going to be talking about sets and other data structures in this course, we want to be careful that our notation really precisely captures what it is that we're talking about. So we're going to introduce the idea that a comma in a data structure alerts us to the fact that we have an ordered structure, that there is like a first one, a second one, a third one, and so on. So the comma separates and orders the objects. If there's no comma, then we're going to consider this data structure to be unordered. The objects can float around. The A and the B can change places. It's still the same object. So sets are not going to have commas. If we do have a thing that looks like a set with a comma, that's going to be for us an ordered set. Okay, so a side has a bar over it. That's just a set. It's unordered of 2 points. An oriented side has a tilde over it rather than a bar, and it means an ordered set of 2 points with a first one and a second one. Okay, so for example, here are now 3 different kinds of ways of combining 2 points. Okay, so here's a point A and a point B, and here is the side AB. And here's how we're going to denote that side, how we're going to geometrically represent it on our page. What it is officially is exactly a set with 2 points. So it's really just the set consisting of that point and that point. But because we want to see that side, we want to be able to recognize it on the page, we're going to join the 2 points with a segment. All right, so that's physically what a side looks like. Here is another thing that we can create from 2 objects. It's one that's already familiar to us. It's a vector, the vector CD. It also involves the point C and the point D, so there's also 2 points involved. But now it's represented by the CD with an arrow on top. Now I draw the arrow with just sort of a half arrow, but sometimes you could maybe use a full arrow. That's fine, just typographical differences. So this vector is, well, we've seen what a vector is, right? It's just a number enclosed in round brackets. And it has the property that if we translate C and D and say move them down there somewhere, then that new vector is going to be the same as that vector there. So vectors are kind of movable. Sides, however, are not, because the point A and the point B are fixed. And now we have this other notion of an oriented side. So here's point E, here's a point F, the oriented side EF. How are we going to represent that? Okay, so the oriented side is different from the side because there's a first and a second in the ordered pair. Really, the E is the first one and F is the second one. That's our convention. The tilde goes from the low to the high, so starting from E to ending in F. And we're going to denote this oriented side with this terminology. So let me introduce that. It's like the side, except that it has an arrow in it, and the arrow we'll put in the middle to try to avoid possible confusion with a vector. The vector has the arrow, which is like an open arrow, at the end. We see that? We see, that's a vector. This is a different kind of arrow. It's like a little closed triangular arrow. And it's in the middle of the side. So those are to try to help us recognize that that actually is an oriented side, not a vector. All right, so these are 3 different ways of creating structure from 2 points, and it's very useful for us to be able to distinguish them, both in terms of notation, in terms of the definitions, and in terms of some symbolic geometrical representation of them. Okay, so now we want to step up from 2 points to 3 points, to go from a side to a triangle. Okay, so definition. A triangle, ABC bar, is a set of 3 points, A, B, and C. Notice that there's no commas, That's telling us that this is actually a set, not an ordered set. So the order of the points does not matter. If we rewrote this as BAC, it would be the same triangle. It would still be represented by this thing here. But it also means that we could rewrite this thing by saying that ABC bar is the same as BAC bar. They are the same because they represent the same set of 3 points. And note again, the absence of commas means order does not matter. That's our convention for data structures. If you're interested in data structures, I have quite a few videos on that in my Math Foundations series. And here is how we're going to picture a triangle. There's A, there's B, there's C. These are points in the plane, affine points. And we're going to represent the triangle just by drawing segments between the 3 points. And that's the triangle ABC bar. Note that a triangle is not an infinite set of points because for us that's impossible to specify. Okay? So we're not referring to all the points, inside here. It's not some kind of list of trillions of points. It's just 3 points. You write down that point, you write down that point, you write down that point in a set. That is what a triangle is for us. That's the definition. We may visualize it like this, like a regular triangle, but that's just how we like to visualize things. That's not really the essential aspect of it. The essential aspect is that it's a data structure involving 3 affine points. And let's note that the triangle ABC bar, there it is, has 3 sides, namely AB bar, AC bar, and BC bar. What are these sides? These are just the subsets of this one that contain 2 points. So there's a natural connection between the triangle and its 3 sides, just as there's a natural connection between a set of 3 objects and the 3 subsets of 2 objects that you can find inside it. Now, just as we had sides and oriented sides, we're going to have triangles and oriented triangles. What is an oriented triangle? An oriented triangle is denoted by this, ABC with a tilde on top. The tilde means oriented. And what is it? It's an ordered set of points. So here's a set, A, B, C, but it has commas. That means that it's ordered. But it's actually ordered in a very particular way. So we're going to say that it's actually cyclically ordered. And what does that mean? Well, that means that it's an ordered set like this, but we're going to agree that we can change the order in a particular kind of way, and the object's not going to change. So we're going to agree that ABC, the set A, the ordered set A, B, C in that order, is the same as the ordered set BCA, which is also the same as the ordered set CAB. Right. So yes, the order matters, but we're also allowing 3 different orders to be completely equivalent or actually equal. That's what an oriented triangle is. So it's a little bit subtle. Here's our notation for an oriented triangle. Again, we have 3 points, A, B, and C. We draw the segments joining them. But to represent the fact that this is an oriented triangle, we're going to draw a little circle inside, and that circle is going to have one of our little closed arrows giving a direction, either a counterclockwise direction or a clockwise direction. In this case, it's a counterclockwise direction, telling us that the orientation is A, B, and then C. Or B, C, and then A. Or C, A, and B. All of those 3 orderings are the same. They all represent the oriented triangle ABC. Those are not all the orientations, of course, right? There's also 3 other orientations. There's the orientation ACB. That would be a different oriented triangle. That would be what we get when we take that circle and we replace the direction of the arrow. Instead of going this way, it'd be going this way. And we, instead of writing ABC, we would then write ACB with a tilde on top. So that would be a different oriented triangle. Okay, so let's also observe that this particular oriented triangle, the triangle ABC, has three oriented sides. It has the oriented side AB, the oriented side BC, and the oriented side CA. So now we know what an oriented triangle is, and that's the key ingredient to be able to define our notion of area. In fact, our notion of signed area. Okay, and so now, very, very important, the really crucial area formula. This is the true area formula upon which the algebraic calculus is built. Okay, so one cannot overestimate the importance of this formula. Okay, so it's, in this case, a very special case. So we're going to generalize this quite significantly, but this is the core. This is the heart of the matter. This single formula here really captures this crucial definition of area. Okay, so what is it? Well, the ingredient, first of all, is an oriented triangle of a rather particular kind. We're looking at the oriented triangle OAB, and you can see the orientation there represented by this circle oriented in this direction, meaning that the order is O, A, and B. Or if you prefer, A, B, and O. Or if you prefer, B, O, and A. Right? But not O, B, A. No, that's not one of the orders. Okay. So the point A is, we'll say, the affine point A, comma B. The point B is the affine point C, comma D. O is the origin, so that's the affine point 0, comma 0. Okay, drum roll. The signed area of the oriented triangle OAB is, and here's the definition, S of OAB oriented, or tilde, is by definition 1/2 of AD minus BC. What are we defining? So we're defining what we mean by the signed area of this particular oriented triangle. It's a rather special oriented triangle because one of the points is the origin. And otherwise we have AB here and we have CD here, and those of you who have taken linear algebra will recognize this kind of thing. AD minus BC, this is a determinant, a 2x2 determinant. It's a determinant of the matrix with entries A, B, C, D. And we're taking a half. And notice a few things. Notice that we're calling this S and not, say, A. I was tempted to call it A, little a, but that's a bit problematic because there's going to be an A in the formula. I actually like using A, B, and C, D as my two basis kind of vectors. And so I like AD minus BC. That's so familiar. Everyone recognizes immediately what that is. So I prefer not to have an A here for that reason. But also I think the S is very useful because it alerts us to the fact that this is a signed area. Okay, the signed aspect of this thing is crucially important. Crucially important that it's not with absolute values. You may have seen this in linear algebra where you take this quantity and then you take absolute values and you call that the area. No, 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 no. Okay, we do not want to use absolute values. It's crucial that this thing can be positive, it can be negative. Of course, it can also be 0. All right, we're going to see the implications here, many, many implications. We're going to build up all kinds of interesting things upon this fundamental formula. And one of the important exercises in this lecture will be to convince yourself that this is not really an ad hoc formula, that actually reflects in a reasonable way in the Euclidean situation what we would ordinarily call the area of this triangle. This is not a new kind of area. This is really corresponding with our familiar notion of area if you say, use the rectangle area formula in the context of Euclidean geometry. So this agrees to more or less, except for the sign, with the sort of rectangle area formula kind of story, but it's more general. And we'll see more flexible and when we go to higher dimensions and many other applications, this will be much better suited for building up a theory of integral calculus, as we will see. Okay, so there's much to learn. I'm Norman Wahlberger. Thanks for listening.